In this lecture, we aim to get a better understanding of the way that forces, especially the force of gravity, affect motion. We will use two key concepts for describing how gravity affects motion. The first is energy. Energy comes in several types. One is kinetic energy, which depends on how things move. And there's also potential energy, which depends on the forces that are acting. And as we'll see, there are other forms of energy as well. The second concept is angular momentum. Angular momentum is a way of measuring the circular motion of a system. The useful thing about these two quantities, angular momentum and energy, is that they are conserved. That is, both the total energy and the angular momentum of a bunch of masses interacting by gravity remain constant over time. Although these ideas are part of Newtonian mechanics, they are not all Newton's own ideas. The Principia was a starting point for a long development of the science of mechanics. And later discoveries often make earlier discoveries simpler and easier to understand. So we will use more modern language and concepts than Newton himself used. And we will describe some ideas that had not quite been worked out in Newton's day. We're going to use mathematical equations as tools for explaining our concepts. But behind each equation, there is an idea, and it is the idea that matters. That's what we care about. So we'll admire the equation, and we'll think about how they work. We may even play around with them and do a simple calculation or two. But remember, the important thing about the math is what it means. The first great idea is the idea of energy. Everybody knows about energy, or they think they know about it, yet energy can be a surprisingly subtle business. It is worth the effort to get it right. So here's the first thing to remember. There are different forms of energy. Three forms, kinetic energy, potential energy, and heat, are particularly important for our purposes, but we'll have occasion to mention several others. Energy can be changed from one form to another or moved from place to place, but the total amount of energy remains constant over time. As physicists say, energy is conserved. One nice thing is that energy is a simple numerical quantity. That is, it might be positive or negative. Some kinds of energy can be negative, but it does not have a direction in space. So we do not have to worry about direction when doing our energy accounting. Our first kind of energy is called kinetic energy, which we'll abbreviate KE. The idea is simple. Objects have energy simply because they are moving. Imagine a car moving along a highway. It has a mass, m, and a speed, v, and the kinetic energy depends on both the mass and the speed. That is, kinetic energy is 1/2 times m times v squared. This depends on the mass, m, so a larger car has more kinetic energy than a smaller car. And a car has a larger kinetic energy the faster it goes. In fact, going twice the speed, doubling v in the equation, yields 4 times the kinetic energy. That's because kinetic energy depends on v squared. If we measure our mass in kilograms and speed in meters per second, the kinetic energy is calculated in a unit called a joule, which is named after the English physicist James Joule. 1 joule is the kinetic energy of a 2-kilogram object, a 2-liter bottle of water, say, moving at 1 meter per second, which would be a moderate walking pace. Now, the kinetic energy of an object is not constant. It might change when a force acts. If I toss an apple upward, gravity slows it down, so its kinetic energy decreases. If I drop the apple downward, gravity speeds it up, so its kinetic energy increases. If the apple is in a circular orbit around the Earth, moving at a constant speed but continually changing direction, then its kinetic energy stays the same. Whenever a force produces a change in the kinetic energy of an object, we physicists say that the force does work on the object. The term work here actually has a technical meaning in terms of forces and movements. But all we need to know for now is that the total work done on an object is the change in its kinetic energy. So if you like symbols, you could write W equals delta KE, where delta, of course, is our symbol for change. This brings up our next kind of energy, the energy associated with a force. This is the potential energy, or PE. Well, what's potential energy? Here are three things to keep in mind. First, potential energy is always connected to some force. Now, our main business is gravity, so we'll talk about gravitational potential energy. Second, potential energy describes the potential of the force to do work. When gravity does work on something, the potential energy changes by the opposite amount. Third, while kinetic energy depends on how things are moving, potential energy depends on where they are. It is energy stored in the location of something. So let's drop the apple yet again. As we will see in a minute, the potential energy is greater when the apple is higher up, lower when the apple is farther down. So at the beginning, potential energy is greater, but kinetic energy is zero. Then as the apple falls, its kinetic energy increases while its potential energy decreases. Now if we add up the two kinds of energy, kinetic energy plus potential energy, we arrive at the total energy. Technically, this is called the total mechanical energy. Remember that mechanics is the science of motion and force, so mechanical energy is the energy due to motion, kinetic energy, plus the energy due to the force, potential energy. So as the apple falls, its mechanical energy stays constant. And this is true whether the apple is going up or down or sideways in orbit around the Earth. So long as gravity is the only force acting on it, kinetic energy plus potential energy stays the same. So to make this more than a hand-waving idea, we need an actual formula for the potential energy due to gravity. But first we need to answer a rather peculiar question. Consider the Earth and the apple as before. When should the potential energy be equal to zero? It's easy to see when kinetic energy equals zero. Kinetic energy is energy of motion, and it's zero when the object is at rest. But where should we put the apple so that it has zero potential energy? The floor? Sea level? The center of the Earth? Each of these answers might make some sense, but we will make a different choice, one that will make everything simpler for us later on. Our idea is to set the potential energy equal to zero, where the gravitational force is also equal to zero. Now, the gravitational force gets weaker with distance, so we will set potential energy equal to zero for the apple when it is extremely far away, effectively at an infinite distance. That's where the apple and the Earth would really be independent of each other. Remember, we said that the lower the apple is, that is, the closer it is to the Earth, the lower its potential energy will be. Lower than zero means negative. So the gravitational potential energy of the apple will always be a negative quantity. The apple falls toward the Earth, its potential energy goes down by getting more negative, further and further below that 0 point. This is not as confusing as it seems at first. It's like discussing temperature on a really cold day. Minus 20 degrees is colder, a lower temperature than minus 10 degrees. We aren't the least bit confused by the fact that 20 is a larger number than 10. That minus sign makes the difference. Minus 20 is lower. Minus 10. Now we are ready for the basic potential energy equation for gravity. So we imagine two masses, m1 and m2, separated by a distance r between their centers. The equation for gravitational potential energy is Pe equals minus g times m1 times m2 divided by r. Okay, let's take this apart and see how it works. The equation is reminiscent of the gravitational force between two masses. In fact, it looks just the same, except that the r in the denominator is squared for force, but not squared for potential energy. and potential energy is negative, as we said. And because R is in the denominator, the potential energy is close to zero when R is really large. The potential energy is about zero for the two masses when they are far apart. And then it gets more negative as they approach each other. So when the apple moves downward, it gets closer to the center of the Earth, so its potential energy gets lower. It gets more negative. Now, when the only force acting is gravity, kinetic energy plus potential energy, the total mechanical energy, stays constant. And that lets us figure out something quite interesting. So throw the apple upward. It goes up, slowing till it reaches the top of its path, where it is momentarily at rest. Its kinetic energy is zero at the top. Then it falls back down. Throw the apple a little faster, and it goes a little higher. At the top of its trajectory, its kinetic energy is zero, which is the smallest possible value for kinetic energy. And in each case, the total energy, kinetic energy plus potential energy, is negative. Why? Well, potential energy for gravity is always negative, even at the top of the arc that the apple travels in. And since kinetic energy is equal to zero there, the total energy is also negative. But now throw the apple upward really, really fast, so fast that it goes very far from the Earth. Out there, Earth's gravitational pull is much weaker, and the apple hardly slows down at all. At very great distances, the gravitational force is negligible, and the apple would fly away at a nearly constant speed. In other words, if you could launch the apple fast enough, it might never fall back to the Earth. But how fast is fast enough? We can define something called the escape speed. That's the minimum speed necessary for the apple or any object to completely escape the Earth's gravity. How fast is that? Well, the problem sounds awfully complicated. The speeds and distances and forces are all changing as the apple goes. However, we actually now know enough to figure out the answer. It requires a couple of steps of algebra, but we should not get too distracted by that. The important thing is to see how the ideas work together. So if our apple thrown up does escape, doesn't come down at all, then it will eventually get to a huge distance from the Earth, millions and billions of miles away. And with such a separation between the Earth and the apple, the potential energy is practically zero. Of course, the kinetic energy cannot be less than zero, no matter how slowly the apple moves. So that means for an apple that is escaping, the total kinetic energy plus potential energy for the apple must be at least as big as zero. Therefore, the escape speed is the speed the apple needs to make its total kinetic energy plus potential energy equal to zero. So, if we let little m be the mass of the apple, big M be the mass of the Earth, and r be the initial distance between the apple and the center of the Earth, we have that 1/2 times little m times v squared, the kinetic energy, minus g times big M times little m over r, the potential energy, equals zero. And we can solve this equation for the speed v. First, we add g times big M times little m over r to both sides, and now we notice that the same little m, the mass of the apple, is on both sides. We can divide it away. That makes sense. The slowdown of the outward moving apple does not depend on its mass. It would be the same for any object. So the escape speed won't depend on that mass either. If we multiply our equation by 2, we wind up with v squared equals 2 times g times big M over r. And now we take the square root to find the escape speed, which we will now rechristen by calling it v sub escape. V escape equals the square root of 2 times g times big M over r. If you find yourself a bit rusty with algebra, that's okay. What we did was not voodoo. We started out with an equation we knew to be true. Kinetic energy plus potential energy equals 0 for an apple that barely escapes. Then we started performing mathematical operations, the same operation to each side of the equation, to make things simpler and to put what we were interested in this case, the speed v, all by itself on one side. And then we were done. We had a formula for escape speed. We can put in some numbers. The mass of the Earth is about 6 times 10 to the 24th kilograms, as Cavendish figured out. The radius of the Earth is about 6,400 kilometers, or about 6.4 times 10 to the 6th meters. And the value of g is 6.67 times 10 to the minus 11th meters cubed per kilogram second squared. This is definitely a job for a calculator. And when we use a calculator, we end up with the escape equaling 11,200 meters per second. That is, the escape speed of the Earth is more than 11 kilometers per second. That is very fast. But if we launch an apple, or anything, upward with a speed this great, neglecting air drag and so on, then it will simply never fall back to Earth. The gravity of the Earth will not be able to keep hold of it and pull it back. What goes up in this case does not ever come down. When we send a space probe to another planet or out into deep space, we use a big rocket to accelerate the probe to more than the Earth's escape speed. The details are more complicated, of course. For example, we also need to consider the gravity of the sun and so on. But that is the main idea. If you go fast enough, you don't fall back ever. We said that the mechanical energy, kinetic energy plus potential energy, stays constant. But that is true only if gravity is the only force acting. When other forces act, we have to take into account other forms of energy. So suppose I throw the apple upward. Where does that kinetic energy come from? Well, the work was done by my muscles. There is chemical energy stored in my muscles, and I release some of it when I throw the apple. So there's chemical energy. We also have electrical energy and nuclear energy and so on. And each of these can be turned into mechanical energy. But the total energy, adding up not only kinetic energy and potential energy, but also all other types of energy, the total energy is always conserved. Energy can change form or be transferred from one place to another, but it cannot be created or destroyed. That's the law of the conservation of energy, one of the most important principles of physics. Now let's drop the apple. As it falls, potential energy is turned into kinetic energy. But when it hits the ground, it bounces and rolls a bit and then comes to rest. Where did the energy go? The answer is a type of energy that we haven't talked about yet. Thermal energy, heat. It turns out that objects have internal energy simply because they are warm. In fact, their temperature is a measure of their heat energy content. Higher temperature means more thermal energy. So after the apple has come to rest, both it and the ground have warmed up by a tiny amount. Potential energy turns into kinetic energy, which then turns into heat. That sounds like a plausible story, but is it true? In fact, we can verify it right here. I have here an enclosed tube containing lead shot. So if I turn the tube over, I raise the shot to the upper end, so I add potential energy. The lead shot falls to the bottom, so potential energy turns into kinetic energy. Then at the bottom, the shot pellets deform and rub against each other so that kinetic energy turns into heat by friction. That means that the lead shot warms up a little bit. So let's see if that really happens. First, we measure the temperature through a little hole in the side. There's our thermometer. Ah yeah, the temperature is about 22.3 degrees Celsius. Now, we turn the tube over 50 times. Now, we measure the temperature again. The temperature is 24.8 degrees. The temperature has gone up by a couple of degrees. Why? because potential energy turned into kinetic energy, and that turned into heat. We have to drop the lead shot a long way, 50 tube lengths, to get a small rise in temperature. That rise corresponds to a pretty large amount of energy. For 1 kilogram of lead, it takes over 100 joules of energy to raise the temperature by 1 degree. For 1 kilogram of water, 1 liter of water, it would take more than 4,000 joules. So heat is a kind of energy. But what kind of energy? Well, consider the air in this room. The air is not moving much, so its kinetic energy appears to be zero. But if we take a look at the air very closely, molecule by molecule, we see that those molecules are actually moving around extremely fast, hundreds of meters per second. We don't notice this because the motions are completely disordered and random in all directions. They move in all directions. But the kinetic energy of that molecular motion is still there. And that kinetic energy is what we perceive as temperature. So heat energy is not really a new and different kind of energy. It is familiar mechanical energy, the energy of the disordered random motions of the tiny molecules that make up the objects we see. Energy is a tremendously useful idea, and it shows up under a variety of units, a variety of denominations, not just joules, but also ergs, calories, kilocalories, British thermal units, those are BTUs, electron volts, watt hours, foot pounds. But all of these are measures of different forms of the same thing, energy. Now, our second great concept from mechanics for understanding gravitational force is almost as handy as energy, and that idea is angular momentum. Let me begin by introducing you to a second cousin of angular momentum, the concept of linear momentum, also sometimes called just momentum. Newton called it quantity of motion. Like kinetic energy, the momentum of an object depends on its velocity and its mass. But the formula for momentum is simpler. P equals m times v. Here, m is the mass of the object, v is its velocity, and we use the letter P for momentum because, unfortunately, the letter m was already taken for mass. Momentum does depend on the direction an object is moving. It is what physicists call a vector quantity. It has both magnitude and direction. The momentum of a body has such and such a value south, or up, or north by northwest, depending on the direction it is traveling. Total momentum, like energy, is conserved. The reason is Newton's law of action and reaction. Suppose an object A exerts a force on object B. Perhaps the Earth is exerting a force on the moon. That causes B to accelerate, to change its momentum. But B also is exerting a force on A. The moon exerts a force on the Earth. That force is of the same size, but opposite in direction. And that causes the momentum of A to change in the opposite way. And so the total momentum of A and B remains constant. That actually suggests a different way of thinking about force. When one object exerts a force on another, they are really just exchanging momentum. That's what a force is, a transfer of momentum. So much for linear momentum. What about angular momentum? Well, angular momentum is a very general idea, but it is easiest to think about in a simple case. So suppose we have a mass m that's moving in a circular path of radius r at a speed v. Then the angular momentum of the mass, denoted by the letter L, is given by L equal to m times r times v. And angular momentum has its own law of conservation. In the absence of external forces, the total angular momentum of a system of bodies stays constant. Parts of the system can exchange angular momentum with other parts of the system, but the total remains the same. Let me illustrate this by a demonstration. So I'm going to sit on a rotating stool, and when I go around, all the parts of my body will move in circles around a vertical axis. Now, the stool has very little friction, so my angular momentum stays constant. I'm holding some masses in my hands, and my hands and arms also have mass. So if I draw my hands inward, the radius r gets smaller for those masses. But the total value of L equal to m times r times v for everything put together must stay constant. The mass stays the same and r gets smaller, so v must increase. In other words, if I pull my hands inward, I must rotate faster. Let's see. Conversely, if I let my arms go outward, I'll slow down. Not because of friction, but because of conservation of angular momentum. Does angular momentum have a direction? Is it a vector like linear momentum? Well, it is a vector, but its direction is a little surprising. As a mass goes around in a circle, it goes in different directions at different times, first north, then west, then south, then east. If angular momentum is constant, then it can't point in any of those directions. But there is one direction that does not change, the direction perpendicular to the whole circle, up. So here's the rule. You curl the fingers of your right hand in the direction of the circular motion, and then your extended thumb points in the direction of the angular momentum. So when I was rotating on the stool, the angular momentum pointed along my axis of rotation. If I went one way, it pointed up. If I went the other way, it pointed down. Earth rotates on its axis from west to east, so the angular momentum points along the axis toward the North Pole. For a planet in orbit around the sun, the angular momentum points perpendicular to the plane of the orbit. We will see angular momentum many more times in the next few lectures. The conservation of angular momentum is a key to understanding all kinds of things. It's an important principle to keep in mind as we explore the way that gravity shapes the universe. We've introduced a couple of great concepts from Newtonian mechanics, and both of these have conservation laws. Energy is conserved. Angular momentum is conserved. And we also said a few words about linear momentum, which is also conserved. Each of these plays a vital role in mechanics and in understanding gravity. Each of these gives us insight into the way that objects move and how different forces, particularly the force of gravity, will affect their motion. Next time, we will return our attention to motions in the heavens to see how ideas of energy and angular momentum apply to motion in an orbit. Kepler, you'll recall, established 3 laws describing how planets can move around the sun. Newton explained these laws from his law of universal gravitation. But how do orbits work exactly? How do the ideas of energy and angular momentum explain the way that stars, planets, and moons move through space? How do these ideas help us predict the motions of artificial satellites or navigate spacecraft from one planet to another? To find out, we will venture into the elegant science of orbital mechanics.